Hello and welcome. Today we're diving into one of the biggest puzzles in data science. How do we forecast the future? I mean, we live in a world that is just overflowing with data that zigs and zags, often with no warning at all. So how on earth can we predict what's coming next? Well, we're going to break down a really powerful tool that helps us find the hidden patterns inside all that chaos. So just take a look at this. This is Google's stock price over time. It is all over the place, right? Yeah, there's a clear upward trend, but day to day, it's incredibly volatile. Trying to predict the exact price for tomorrow, let alone a month from now, it honestly seems impossible. But you know what? This is exactly the kind of puzzle that data scientists live for. And their secret weapon for tackling it? It all starts with a surprisingly simple idea. Here's the thing. Before you can predict anything, you have to find some kind of stability. You just can't build a model on pure, random chaos. So the very first step in forecasting a time series like this isn't actually to model the trend itself, it's to figure out a way to strip that trend away so we can see what's really happening underneath. And that brings us to a really crucial concept. And that concept is called stationarity. Now that might sound complicated, but the idea is simple. A stationary time series is one that, statistically speaking, is kind of just chillin'. Its average value stays the same, how much it bounces around that average stays the same, and its relationship with its own past values, that stays the same too. It's stable, it's predictable, and it is the perfect foundation for building a forecast on. So let's break that down. You've got these two states. On one hand, you have stationary data. That's our goal. It's stable, it's predictable, it's much easier to work with. But on the other hand, you've got non-stationary data. This is the stuff that has trends or seasonal patterns with properties that are always changing. In other words, it's the real world. That Google stock chart we just saw, oh yeah, that is totally non-stationary. So the big question is, how do we get from one to the other? Okay, so for just a minute, let's pretend we live in a perfect world where our data is already stationary. How would we model it? Well, it turns out we have two main building blocks that we can put together into a pretty powerful toolbox. First up, you've got the autoaggressive part, or AR. This one is super intuitive. It basically assumes that what happens next depends on what just happened. It's kind of like driving by looking in your rearview mirror. Then you've got the moving average, or MA component. Now, this part is pretty clever. It looks at the errors your past forecasts made and uses those mistakes to make a better guess next time. It literally learns from its own failures. And when you combine these two, you get what's called an ARIMA model, a fantastic tool for forecasting stable, stationary data. But, and this is a big but, here's the catch. The ARIMA model is great, it's powerful, but it has one non-negotiable rule. Your data absolutely must be stationary. It just doesn't know how to handle data with a trend, like our Google stock chart. So, are we stuck? Not at all, because this is where our model gets a superpower. The solution is actually so simple and so brilliant that it just adds a single letter to our model's name, but that one letter changes absolutely everything. So, let's look at our problem again. We've got this strong upward trend, right? The average price is clearly not constant. To make this thing stationary, we have got to get rid of that trend somehow. And the secret ingredient is the letter I, which stands for integrated. But really, what it means is differencing. Instead of looking at the actual stock price every day, we're going to look at the change in price from one day to the next. Think about it like this. If you're trying to track your weight, the total number might be trending up, which is hard to predict. But if you just look at the daily change, plus 1 pound, minus half a pound, that series of changes is probably going to hover right around zero. It becomes stable. And would you look at that? This is the amazing result. After we apply that one simple trick, just calculating the day-to-day change instead of the total price, this is what our data looks like. The crazy upward trend, it's completely gone. The data now just bounces around a steady average of zero. We did it. It's stationary. We've turned an impossible problem into one we can actually solve. And so that's the whole shebang. ARIMA, ARIMA. It stands for Autoregressive Integrated Moving Average. We use the I, the differencing, to make our messy real-world data stationary. And then, once it's stable, we can use the AR part, our rearview mirror, and the MA part, our error correction, to build a powerful model. It's a complete, elegant process. All right, so enough with the theory. Let's put this into practice. How do we actually take this ARIMA model and apply it to our Google stock data to build a real forecast? Well, it's not just guesswork. There's a very systematic method for this.
Statisticians call this process the Box-Jenkins method. It's basically a three-step dance. First, you identify. You look at your data and figure out the right parameters. How much differencing do you need? How many past values for the AR part? How many past errors for the MA part? Second, you estimate. You let the computer do the heavy lifting, fitting the model you chose and finding the best numbers. And finally, you do some diagnostic checking. You look at the mistakes your model made. Are they just random noise? If so, perfect. If not, you go back to step 1 and refine your model.
Now, for that first step, identification, we don't just have to guess. We can have a computer test a whole bunch of different combinations for us. And for each model it tries, it calculates a score called the AIC. You don't need to worry about the complex math behind it. All you need to know is one simple rule. The lower the AIC score, the better the model is. It's a really smart metric that balances both accuracy and simplicity. And looking at our table, we have a clear winner. The ARIMA 110 model has the lowest AIC score of them all. So what does that tell us? It confirms we need one level of differencing, one autoregressive term to look at yesterday's change, and 0 moving average terms. We've found our champion model. Okay, next up is the diagnostic check. These funky-looking plots show us the model's errors. Statisticians call them residuals. What we want to see here is basically just random static, like an old TV with no signal. If we saw clear patterns in the errors, it would mean our model missed something important. Now, is it perfect? Not quite. We can see a few spots where the errors are clustered. But for the most part, the model did a great job capturing the underlying pattern, leaving mostly random noise behind. So we've identified our model, we've estimated it, and we've checked it. Now comes the moment we've been waiting for, the forecast. But this is also the point where we have to be really honest about what any model can and can't do. And here it is. The black line is the actual history of the stock price, and that blue section is our model's forecast for the next 100 days. The solid blue line in the middle is its best guess. But look at how the shaded areas around it get wider and wider over time. That is what we call the cone of uncertainty. It's the model telling us, very humbly, hey, the further out I try to predict, the less certain I become. And honestly, that is the most valuable thing a forecast can tell you. So to make this really concrete, the model gives us probabilities. It's essentially saying there's an 80% chance that the real stock price, whatever it ends up being, will fall somewhere inside that darker blue cone. So you see, it's not giving us a single magic number. It's giving us a much more useful and realistic range of possibilities. So what's the big takeaway here? An ARIMA model, it's not a crystal ball. It can't predict a surprise news event or a sudden crash. But what it does give us is a powerful, rigorous method for finding stability inside of chaos, for learning from the patterns of the past, and maybe most importantly, for quantifying our own uncertainty about the future. It replaces pure guesswork with a calculated range of possibilities. And in a world as unpredictable as ours, that is an incredibly powerful thing to have.